Welcome to this lecture in which we are addressing efficient HVAC systems in moderate and cold climates, meaning that we essentially look at heating. We will address mainly small buildings like houses or small offices. The main difference with larger buildings is the air handling unit. We addressed air handling units in many other lectures. In this one, we don't address hot tap water either, only space heating. In cold and moderate climates, heating is needed. As described in other lectures, reducing the heating demand is essential to lower the peak load and the heating demand, which is essential to connect to renewable energy. Reducing the heating means insulating and limiting air infiltration. High levels of insulation are not so much of a problem in new build. However, in existing buildings, which in many countries represent a vast majority of the building stock, that is not that easy. Easiest is insulation of roof from inside and of floor from underneath if there is a crawl space. Underfloor insulation is possible too. Changing glazing for highly insulated glass like triple glass is also a relatively easy to take measure from both costs and technical perspectives. Insulation of outdoor walls is much more of a problem. Outdoor insulation is the most effective but is costly. It changes the appearance of the building, takes space on the sidewalks for which a permit will generally be needed. In apartment buildings with owner associations, it must be done at once for all apartments. Much easier is indoor insulation. However, indoor insulation, if not professionally carried out, may result in humidity problems. And most important, it reduces the living area. High insulation means a high thickness, and especially in small houses, living space is very important. Of course, there are also many developments in thin insulation, like vacuum panels, but still their price and vulnerability makes that they are not widely used yet. So, there is still a challenge here. Reducing infiltration losses may be done by using special constructions for the window frames and by sealing cracks. If it is good to reduce infiltration, it is always wrong to reduce ventilation below what is necessary to ensure a good indoor quality. There should be continuous flow of ventilation air, not only in large buildings using sophisticated air handling units, but also in smaller ones. This means that clean air should be supplied in all rooms where people stay for longer time. In view of energy efficiency, is heat recovery from exhaust ventilation air a must, meaning that supply and exhaust mechanical ventilation is needed. Generally, it is done centrally in a balanced ventilation unit like this, which is a small air handling unit with only a heat recovery heat exchanger. Sometimes it can also be done locally in the wall or window of each room, like that. In summer, in climates where outdoor temperatures are high, the heat recovery can also be on, or if there is a cooling system in the house. Otherwise, the heat recovery should be bypassed, as the indoor air will probably be warmer than the outdoor one. But in general, the system above is used, and clean and pre-warmed air is brought through valves into each room. It is generally exhausted to the heat recovery unit through ducts in bathroom and toilet. There are good designs and bad designs. Poor quality air valves will cause draft. Too high air velocity and too many bends will cause noise. Dirty ducts and filters in the AHU will cause pollution, so a careful design is needed. If the fan is too close to living areas, like a sleeping room or on the attic, there will be noise burden unless the fan is extremely well acoustically insulated, which is highly recommended. Unfortunately, in many of these systems, there is only one central flow rate control, meaning that all rooms are equally ventilated. But in general, at night, people are in the sleeping rooms and not in the living room, and conversely. A zone control, for instance one zone being the sleeping rooms, the other one the living room and kitchen, is better but does not account for the flexible use of rooms. Sleeping rooms are often used as study rooms, so in the end, control per room is much better, like this. It can be aided by CO2 control. A CO2 sensor, CCO2, measures the CO2 concentration. If the CO2 increases above a certain level, CO2 set, for instance 800 ppm, indicating too little ventilation, the ventilation will be switched on. There are also systems in which the supply ducts to the rooms are suppressed and the air is centrally supplied, in the staircase or corridor for instance, and it flows through a space under the door or through grills through the rooms in which the fan is on. For the part of the heating demands that is not covered by the heat recovery, emitters are needed, either medium or low temperature radiators or floor heating. The choice and sizes will depend on the degree of insulation and on the heating demand. The degree of insulation influences the heating demand but also the surface temperature of walls and therefore the mean radiant temperature. You've learned in other lectures how to size radiators accounting for this. There is in general a central thermostat controlling the heater and the circulation pump. The thermostat is often placed in the living room and controls therefore the temperature in the living room. So the temperature in the other rooms will be different. That's why there are valves on radiators, either simple ones with manual control of the flow like this, or thermostatic valves controlling the flow based on the measured air temperature close to the radiator, like that. The temperature sensor is part of the valve. The set point temperature depends on the number chosen on the valve. As for floor heating, it should be zoned as well, as temperature preferences are different in living room and bedrooms. Temperature control is similar to the one of the radiators, and people should be aware that when changing the thermostat set point, it will cost a while before the temperature has increased or decreased. So when expecting a cold day, the thermostat set point may be increased in advance, and conversely, in advanced systems, this can be done using predictive control based on weather prediction. Let's look at the generators now. You may remember that for the generation of heat, 6 options are available. Electrical resistance heating, although cheap, is not really recommended. Heat pumps, also electrical, are in general more efficient. We saw that combinations of heat pumps with electric resistance heating for the peak load are a good option, or a peak load combustion boiler may also be used. In other lectures, we dismissed boilers as main generators as they are using fossil fuel. In a more nuanced approach, switching from coal boilers to gas boilers will be a real improvement in terms of CO2 emissions and air pollution. But in a transition, it may be much better to immediately switch to sustainable options. Burning biomass in a boiler is also possible. For instance, using wood pellets. When wood is fully available and comes from maintenance of forests or hedges, and the location is isolated, by which air pollution by particulate matter is not such an issue, that could be a good option. However, in general, one should be very cautious about biomass as, regardless of sustainability labels like FSC, the Forest Stewardship Council, it leads much too often to deforestation, use of fertile ground for non-food aims, and local emissions. Next to the heat pump solution, there is geothermal and solar heating. Solar heat is an intermittent source of heat, needed buffering to cover the hours without sun. Except for the use of pumps in geothermal systems, they are considered to be emission-free. As for waste heat, it depends. Although it is good to reuse waste heat, one should consider that the use of waste heat from fossil fuel industry may lead to maintaining a fossil fuel-based economy and is therefore questionable. Heat pump-based generator combinations for buildings will be handled in more details in another lecture. Resource depletion and CO2 emissions of electrical systems like heat pumps depend on the way electricity is produced. A heat pump is never a sustainable solution on its own. You see here the kilogram of CO2 emitted by the production of 1 kilowatt-hour of electricity in diverse countries. If we take a cold country like Norway, producing almost all its electricity with hydropower, CO2 emissions and resource depletion are almost zero. For a country like the Netherlands, where more than 70% of the electricity production is still based on gas and coal, CO2 emissions and resource depletion are considerable. In this case, waiting for a greener central electricity production in which wind will play a main role, mitigation at building level can be tried. Photovoltaic cells can be placed, delivering a part of the electricity needed when the sun shines. In another lecture, we studied briefly this house, typical of a moderate cold climate. Let's look at the well-insulated version and the passive house version of this house, both suitable for heating by heat pumps. The roof area oriented to the sun is 70 square meters. In both cases, we assume that 3000 kilowatt-hour electricity is used annually to power lighting and household appliances. The annual heating demand in the well-insulated house is 15,066 kilowatt-hour. In the passive house, it is only 5,014 kilowatt-hour. If we use a heat pump with seasonal COP4, we then need 15,066 divided by 4, which is 3,767 kilowatt-hour electricity for heating in the well-insulated house, while we come to 1,254 kilowatt-hour in the passive house. So in total, 6,767 kilowatt-hour electricity is needed in the first version and 4,254 in the passive house version. We now want to place PV cells on the roof. Modern PV cells have an electrical annual production of 150 kilowatt-hour per square meter in the Netherlands. So in the well-insulated version, we need 45 square meter PV cells, and in the passive house version, a bit more than 28 square meter, which is very well feasible. It is not because the PV cells are producing annually the same quantity of electricity as needed by the heat pumps, lighting and appliances that no electricity from the grid will be used. Electricity is also needed at night, and during the winter the PV cells will certainly not produce as much as needed. You see on the left a typical profile for spring and summer, where the PV cells produce much more than needed, while in winter, when the electricity demand is higher because of the heat pump, the PV cells produce much less. At the times where there is an excess of production, it can be either delivered to the grid, if that is allowed in your country, or stored in batteries. When more electricity is needed than produced, the batteries can be activated, or electricity from the grid will be bought. Note that current batteries can bridge no more than a few days, by which there is still a big problem in winter. There are also systems in which the surplus electricity is stored as heat. If the quantity of electricity produced by the PV cells over 1 year equals the annual electricity demand for heating, lighting and appliances, we speak about a net zero energy building, NZEB. If the electricity grid is not sustainable, the consequence is that the building will still use fossil fuels through its electricity use. In this lecture, we addressed important aspects of an efficient HVAC system for small buildings in cold countries, from heating demand and indoor air quality to emitters and their zoning and control. We very briefly addressed the heat generators, ending up with electricity production and possible use of local PV cells where the national grid is not sustainable. Thank you for your attention. Goodbye.